Hello, my name is Mark, and in this video I want to present my system board for Intel 8080 CPU. This board. 8080 is almost 50 years old CPU from Intel, and it's a direct processor for famous well-spread Intel's x86 family. And it is also next logical step for me to develop that board after my previous work around 8008 CPU. So let's get started. And as usual, I want at first to understand what kind of signals do we need to provide to CPU to make it works. And we can see that it need to use different voltage levels. Plus 5 volts, minus 5 volts and plus 12 volts. So at least we need to provide that power signals to CPU. And also we can see different group of signals: data pins, address pins and control signal pins. So we also need to provide them. Clock signal is also going to be generated by my hardware. And I want to run fastest Intel's CPU, 8080A-1, and it runs on very high clock rate in comparison with that legacy CPUs, with more than 3 MHz, 3.125 MHz, if we want to be precise. So after determining what kind of signals I need to provide to CPU, I can start to design basic system diagram for that CPU. As usual, it would be some central piece, some microcontroller or FPGA that would provide memory interface to my target processor. Also, we need to provide power, as I mentioned, and probably that's all. Quite a simple system diagram as usual. After I drew that schema, I had to make a choice about primary components on my board. And the heart of the board, memory controller, could be either microcontroller or FPGA. Yeah, potentially some high performance microcontroller can service target device with such high frequency as 3 MHz. But FPGA would be more convenient, especially because I don't need any complex logic. We just need to service memory operation from target device, and it would be quite a few lines of Verilog code. It is good especially because I have not touched any complex FPGA logic for almost 20 years, so I wanted to keep it as simple as possible. So we have chosen FPGA as a platform, but what concrete vendor or brand of FPGA chip we want to use? I built a list of criteria, and the first point is that this FPGA device should be highly integrated. It should have some ESRAM blocks, and it's better to have flash memory inside it, so I don't need any external flash chips, flash memory chips or SRAM chips. Second point is that it should be enough such integrated memory, because 8080 CPU can address up to 64 kilobytes of memory, so FPGA should provide enough memory for that. Third point is that it should be possible to solder the chip. I don't like to solder BGA packages, so it should be either QFN or QFP packages, something like that. And last but not least, it should be possible to use some open source or cheap tools to work with the device. I don't want to buy some vendor programmers or vendor tools just for that one project. Other components are not that important. For USB to UART bridge, I have chosen a STM32 microcontroller. Yeah, it is overkill, but I wanted to have some kind of backup plan if something went wrong. I always can route some spare pins of that microcontroller to FPGA itself, to target device, or to solve some problems in software mode. So that's why I did that choice. There is a variety solutions to switch from 5 to 3.3 volts. So I have chosen just some standard bus transceivers and level shifters. But it is another story for 12 volts, especially because it is high frequency signal, it is clock signal. So I selected some gate driver to do that. But spoiler alert, I chose wrong one. PCB is quite simple and straightforward. It is just two-layer PCB with some basic routing, nothing special. So let's start soldering. I want to share my mistakes as part of that video. Most of them are quite basic, but some of them were quite tricky to debug, at least for me. So, first mistake was very basic. It's just about picking a wrong footprint. I picked Imperial 2512 instead of metric 2520. And it was a big difference between the two dimensions. As you can see, I had to try to fit my pre-ordered inductors into such big placement. Usually I try to check some parts of board before I solder all components. For instance, I try to check power rails, because it's quite important. If there is some short, or maybe wrong voltage comes to wrong chip, it could just burn innocent component, and it could be quite costly. So that's why I'm doing probing that power rails, and found out that 3.3 volts rail was not working correctly. But it was just a matter of resoldering power IC. After I solder all chips, I like to check if they are soldered correctly. So I'm using some physical probe to try to interact with chip pins, because visual inspection is good, but it not always panacea. After all soldering job, I want to check if system is operational, just from basic software perspective. I had two set of JTAG pins, one set for microcontroller and another set for FPGA. So I attached my JTAG probe and connected to microcontroller via OpenOECD, and it's worked okay. So partial success. But I had some issues with FPGA. It was not responsive, at least for first tries. But later I investigated and my OpenOECD config was wrong. So I had just to add support for TRST pin, which informs FPGA that it should be on a reset state. Next step was to write some code and to upload it into microcontroller and FPGA. For microcontroller it is an easy task because we already have JTAG working, but for FPGA it's a different story. As I mentioned, I wanted to try to avoid usage of some proprietary vendor tools like Flash Pro for my case. So that's why I tried to use same JTAG probe to flash bitstream into FPGA, and it was successful. Yeah, I had to write some simple software to do it from my PC, but it was quite simple. So I would attach a link to repository with that software in description. I'm going to record whole another video about software part of that project. But right now I want to touch one software detail which is related to hardware bug that I introduced. Almost first piece of code that I wrote was interface for the RAM. I just wanted to check if latency is good enough and if we can access a whole 64 required kilobytes of memory. And while testing I saw some strange results. There were some random errors while I tried to read RAM memory from PC, from my controlling software. I debugged that issue, but could not find an error in my implementation. So I attached a oscilloscope, and quick enough I saw just that baud rate for UART was wrong. And baud rate is derived from main clock signal, main fabric clock signal, which I used almost in all blocks in FPGA. And this main clock signal was generated by an internal oscillator. So I found out that it's not that precise. Initially I have used a loud frequent crystal and attached it to FPGA. But because internal oscillator became not that precise, I had to replace it with higher frequency crystal, 16 MHz. And after that it solved my issues. I got working UART, I got working RAM interface. Okay, I got working interface with memory, I got working interface with PC and controlling software. So next step was the most interesting step. It is interface with 8080. And I started with clock signal. And it was quick enough to understand that for some reason I designed totally wrong. I mean, I just used the wrong pins for gate driver. And I have no idea how I did that, but it was quick but ugly fix. After that fix, I saw first traces from 8080 and they made some sense to me, so it was good sign. But a new issue occurs. After some time, maybe 10 or 20 seconds, clock signal just disappears. And it disappears from a gate driver. So I was stupid enough to think about some strange explanation why it's going on. Like maybe some power issues or whatever else. And only after a couple of days of debugging I touched it and it was very hot. So issue was obvious. Frequency was just too high for that particular gate driver. So I had to switch to another gate driver which is suitable for such high frequency applications. Fix is ugly as usual, but it's working. Okay, now I had good and stable clock signals, so it was time to investigate interaction between FPGA and 8080. And the signals from 8080 side were perfect. It totally made sense to me. But when 8080 requested some data from memory, FPGA returned nothing. It was quite trivial to find that issue with voltage level shifter IC. So I have used a very standard Texas Instruments logic shifter, and one side of it should have higher voltage than another one, and I mixed up that sides. So I had to make another modification of my PCB and had another ugly wires all over my board. But after that I got success, and my Hello World example started to output data to my terminal. It was last mistake. After that all my torments with hardware part of the project was finished. So I started to write some programs to test performance of 8080. And I am going to talk about that in my next video. It would cover software implementation, I mean firmware for microcontroller, Verilog code for FPGA, controlling software, all that kind of stuff. But more interesting part would be about running some benchmarks on 8080. In particular, I am going to show results of dry stone and core mark. These benchmarks are using even for modern CPUs and mobile phones, so it will be quite fun to compare 50 years old CPU with fresh 1 year, 2 years old processors. Thank you for watching, and you can find all related source code and project details in description. Bye.